Okay, this video we're going to be talking about asymptotes and wholes of rational functions. Let's start by just looking at an example of a rational function. For example, if we have f of x equals 2 over x plus 3. If we were to find the domain of this, we would say that the domain is that x cannot equal -3, because that -3 value would create a division by 0. Now what this video is going to do is it's going to show what this really means. It's all fine and good that we understand that we can't divide by 0, and whatever causes a division by 0 needs to be restricted from the domain. But just visually, what does that mean for the graph? Well, it can mean a bunch of different things depending upon the factor and where the factor is located and what exponent the factor has, and if it both shows up in the numerator and denominator or not. But what essentially the domain or the restricted domain is going to result in is something called a point or points of discontinuity. And what a point of discontinuity means is that if you were to take a look at a graph of a function, a point of discontinuity would be the place where you would have to lift your pen up in order to continue your graph or tracing the graph. For example, if I had a graph that looked like say something like this. And let's say that this was when x is equal to 2. If I traced this, I would be going along and then tracing it down, and then I would have to pick up my pen and then start back up and then continue it. So when x is 2, there's a point of discontinuity. There's a sort of you'd have to jump. Your pen would have to jump off the page. That's one kind of an example of a point of discontinuity. Another example is when, say, you're going along and then there's a hole in the graph. Let's say this was when x was 4. So for this one over here, you're putting your pen to the paper and you're tracing the graph and everything is going on continuously. Remember, it's all about continuity, which is continuous tracing. So we're going all the way across except until I get to 4. Once I get to 4, there's a hole in the graph. So I would have to jump over that hole to continue. So that would also be a point of discontinuity. So this is a hole, and this over here is something called a vertical asymptote. A vertical asymptote is a point of discontinuity, and so is a hole. They're labeled a little differently though. A vertical asymptote is referred to as a non-removable discontinuity. And what that means is if I redefined, or if I gave a particular value, an output value for when x was 2. Let's say I said that 2 really did have an output and it was 2, 1. It really had a point right over here. If I redefine that value, is it going to make the graph continuous? The answer is no. I'm still going to have to pick up my pen hit 2 and then pick it up again and then start it all over. So even if I were to fill in or define the value at the point of discontinuity, it still wouldn't make it continuous, as opposed to a hole over here, and this is referred to as a removable discontinuity. Now for this one, if I were to define or give an output value for when x was 4, and I defined it as that output right there, it would then make it perfectly continuous. It would go all the way through and it would be a continuous graph. So you can kind of think of it as if the graph looks like it was something was removed from the graph, like a value was removed, which causes a hole in the graph. It's a removable discontinuity. So that if you were to redefine it, or sort of fill in that hole as it were, the graph would then become continuous. But a vertical asymptote is non-removable, because if you were to define it at that point of discontinuity, it wouldn't matter. Okay, so there's a lot of vocabulary there and a lot of definitions, but essentially the restrictions for the graph, the restrictions in the domain, will either result in a non-removable discontinuity in that it would be a vertical asymptote, or it would be a removable discontinuity in that it would be a hole. Now, how do you know if it's going to be a vertical asymptote or if it's going to be a hole? Well, there's some rules when it comes to that. So for vertical asymptotes, and holes, I'll put different rules for both of these. So for vertical asymptotes, if there's only 2 times when it will happen. In fact, there's only 2 times for both of these. If the factor only shows up in the denominator. For example, and I'll do a little example under all of these. For example, let's say I had a function f of x equals 3 over x plus 1. For this one over here, the factor that contains a variable only shows up in the denominator. So this restriction of x cannot be -1 will result in a vertical asymptote when x is -1. So the equation of the vertical asymptote is x equals -1. Now the second time when there would be a vertical asymptote is if the factor shows up in both numerator. I'm just going to put n and d for numerator and denominator. For numerator and denominator, but with a higher degree in the denominator. Now that looks confusing, but when you look at a specific example here, it won't be that bad. So let's say I had f of x equals x plus 1 times x minus 3 over x minus 3 squared. So what's the factor that would create a potential division by 0. That would be the x minus 3 here. So for the domain, we know that x cannot equal 3. Because if it did, 3 minus 3 is 0, 0 squared is 0. We'd be dividing by 0. It's got nothing to do with this x minus 3 up here, though. It has to do with this factor down here. So this factor of x minus 3 shows up in both the numerator and the denominator. Now the question is, does it have a higher degree in the numerator, denominator, or do they have the same degree? Well, for this one, it has a higher degree in the denominator. When that happens, it creates a vertical asymptote. And the equation of it is x equals 3. Now again, if you look at the little sketch I made up here, a vertical asymptote, it's essentially an imaginary dotted line that's vertical here. It's a vertical asymptote. There are such things as horizontal and slant asymptotes, which we'll get to later. Okay, what about holes now? So, if the factor shows up in both the numerator and denominator with the same degree, it will cause a hole in the graph. And an example of that, f of x equals 3 times x plus 1 over x plus 1. Now if we're looking at the domain, we know that x cannot equal -1, because that would cause division by 0. And that same factor, x plus 1, occurs in both the numerator and denominator of equal degree. This is to the first power, that's to the first power. That means there's a hole when x equals -1. So let's look at the second time when there's a hole. So if the factor shows up in both the numerator and denominator with a higher degree in the numerator, that will also cause a hole. So f of x equals x times x plus 5 squared over x plus 5. So looking at the domain here, we know that for the domain x cannot equal -5 because we'd be causing a division by 0 here. This factor of x plus 5 occurs in both the numerator and denominator, but if you see, the numerator is a higher degree than the denominator, which is a 1. And that's going to be causing a hole when x is -5. Let's talk about horizontal asymptotes and slant asymptotes. Let's go through the rules for these, because and again, these asymptotes are just imaginary lines that kind of frame where the graph is going to go, and I'll go through that a little more in the next videos. So let's start just by looking at what a rational function is, which we already did that in the beginning, but I think it's important that you guys look at this while looking at the different rules. For all of these rules, what we're essentially going to be doing is we're going to be comparing the degree of the n of x and d of x polynomials. Again, remember, the rational functions are just a quotient of polynomial functions. So we're going to be looking at the polynomial in the numerator and the polynomial in the denominator, and we're going to compare the degree of them. So here are the rules. First, well, there's 3 rules. If the degree of the numerator is less than the degree of the denominator's polynomial, then the horizontal asymptote is y equals 0, the x-axis. Let's look at a specific example. Say if we had f of x equals 3 over x plus 2. This degree is a 0 degree, because if I were to write down an x, it would essentially be 3x to the 0. The degree down here is 1, because the x value here has a degree of 1. The degree in the numerator is less than the degree in the denominator. So for the graph of this, the x-axis is going to be asymptotic. It's going to have a horizontal asymptote. And we already talked about vertical asymptotes and holes. This will also have a vertical asymptote when x is -2, because that would cause a division by 0. So the graph of this one over here, if I were to just do quick axes here, there would be a vertical asymptote at x equals -2. So that would be the vertical. And there would be a horizontal asymptote, which is the x-axis. And we'll take a look at, how to graph these. But I think, the frame is really important for the picture. It tells you, the boundaries of it. So let's look at the second rule. And I'm going to abbreviate these a little bit instead of writing all this down. So if the degree of n of x equals the degree of d of x, so if the numerator's degree is equal to the degree in the denominator, then the horizontal asymptote is y equals the ratio of lead coefficients. So this might look confusing here. Y equals the ratio of the lead coefficients. But it's not. It's really not bad at all. Just let's look at a quick example here, and I'll show you what I mean by that. So let's look at the degree. The degree up here is 2. The degree down here is 2. So it's a second degree polynomial divided by a second degree polynomial. So if they're equal, then the horizontal asymptote is y equals the ratio, so we're going to have a fraction, of the lead coefficients. So what's the lead coefficient here? 2. What's the lead coefficient down here? 1. So my horizontal asymptote is y equals 2. So it's not bad. You're basically just picking off, if they're already written in proper form, you're picking off the lead coefficients and you just write that down. Let's just look at this one for a second here. So y equals 2, say it's 2 right here, that's going to be a horizontal asymptote. Now x squared minus 1, this, if I factor that, it's x plus 1, x minus 1, so that means for the domain of this problem, x can't be 1 or negative 1. So 1 or negative 1. So both of these are going to be vertical asymptotes. And they would not be wholes because x plus 1 and x minus 1 don't show up as a common factor in the numerator. Alright, last, the only other possibility, right? If the degree of the numerator's polynomial is greater than the degree of the denominator's polynomial, then there is no horizontal asymptote. There is a slant asymptote. Now what a slant asymptote is, it's exactly what you would assume it to be. It's not a vertical line, it's not a horizontal line, it's a line that has some kind of slope. The slope could be 2, it could be negative 5/4, it could be anything except for it having no slope or 0 slope. So an example of this, say we had x squared minus x minus 2 over x minus 1. So if I'm looking at the degree here, the degree is 2 in the numerator and the degree is 1 in the denominator. So it's larger in the numerator than it is in the denominator. So what you need to do is you actually need to divide the numerator using long division by the denominator. And what this does is it will give you the equation of the line that is the slant asymptote. So using long division, and if you don't remember how to do long division, you should refresh yourself. What times x is x squared? Well, that would be x. So you put that up here. And then you multiply this x by both of these values. So x times x is x squared. X times negative 1 is negative x. So we put the line here. We change these signs and we add down. This is going to cancel. This is going to cancel. And we drop down the negative 2. So we actually have a remainder of negative 2 here. So what is the equation of the slant asymptote? It's y equals x. Now you might ask, well, what about the remainder? Well, you throw out the remainder. So the equation of the slant asymptote is the quotient of the numerator and denominator. It's the quotient and then minus the remainder. So in other words, divide the n of x by d of x, divide, and your answer, remember your answer is the quotient, and your answer minus remainder is the equation. Now obviously you have to put y equals. So your answer, maybe I should just put and y equals your answer minus the remainder is the equation of the graph. The equation of the slant asymptote. So if I were to look at this over here, if I were to factor the numerator, let's sort of bring this down here. If I were to factor that out, I would have x minus 2x plus 1 over x minus 1. So because the numerator's exponent, or the degree of the numerator, is larger than the denominator, it's not going to have any horizontal asymptotes. It will have the slant asymptote. So the slant asymptote was y equals, we saw it was y equals x, and we threw out that remainder of negative 2. So y equals x is the slant asymptote. And we see over here that we will have a vertical asymptote, and any vertical line is x equals a value, so x equals 1. So if I were to take just a quick look here, and then we'll be finished with this video, the slant asymptote is y equals x. So that's going to look like this. That's y equals x, that's your slant. And then at 1, you're going to have a vertical asymptote. And these would be the only asymptotes for your graph. And again, it would not have a hole anywhere because this factor of x minus 1 doesn't show up anywhere else.